Hi everyone, welcome to UQ Computing Society's Tuesday night event. Today we have Polymathian here to talk about power station data streams and self-serve compute. So without further ado, I'll let them get started. Thank you.
Thank you. Evening everyone. So we're going to start with the self-service compute. My name is Mitchell Grass. A little bit about myself. I'm a technical manager at Polymathian. Been there about 5 years. I started out as a casual dev while I was a student here at UQ. And nowadays I manage our framework team and our DevOps team, and that involves doing a lot of interesting stuff with our large-scale mathematics that we do as a company, and sort of enabling the other software teams to be able to do that in an efficient manner. And one of the things that we've done for them recently is providing access to on-demand compute. So the problem we had was that we as a company solve a wide variety of computational problems in the mathematics space. The runtime of those can be sort of on a huge variety of timescales, anything from seconds or minutes all the way up to several days with 100% on several cores. And the memory consumption of those tasks can be on the order of megabytes to hundreds of gigabytes, and usually they're CPU bound, but in some cases we have interesting quirks in the third-party software we use where actually having too many cores can slow it down. So that introduces some interesting sort of constraints to work within when trying to design a system to provide compute to these services. The other issue is the computational complexity of the problems. So the tasks are usually ON or worse, which on its own is okay, but with our products the users have an enormous amount of flexibility, and with that flexibility they have pretty well complete control over the input data size, which means that they can develop data sets which end up taking much longer to run than we originally intended the system to do. So the existing setup we had, we've been doing this for quite a long time, and essentially we had the standard pre-provisioned cluster of AWS high-performance machines. Those machines were full of containers. Each container was watching a queue, and as a user clicked a button to put a job onto a queue, one of the workers would pick that up. It had a lot of pros, and sort of that's why we started there. The biggest one being the simplicity. It's very, very easy to manage, it's easy to deploy, you can see the machine, you know what's happening at all times. If something goes wrong, you can SSH into it and have a look. And the other big pro is that the compute's available instantly. So because the code is already spun up, it's already connected, it's already watching, the task can start with sort of a moment's notice. And that allowed us to do a lot of things that maybe in hindsight could have been two separate systems, where we have one system solving these very, very large, massive scale, multi-day computations, and we're using the same system to do 10-second jobs like importing a file. And that led into some cons that we discovered with the system. So a big one was that concurrency limit. So you have to pre-provision how many workers you want to have on the machine. If you over-provision, you're wasting resources. If you under-provision, you could block the ability to upload files based on how many large-scale solves are running. And there are workarounds for that, but it is a problem. It also costs a lot. A big problem with it is that you're paying 24/7 for something that realistically we're only using sort of in bursts during business hours on weekdays most of the time. But we didn't have the ability to only work within those hours and just say turn off the machines at night. It had to be available all the time, but in reality the utilization was pretty low. But then when we did have those bursts and when it was being utilized, it was being utilized really heavily. So those can introduce issues with noisy neighbors, where certain solves or certain tasks might be consuming an unreasonable amount of memory and causing out-of-memory errors on the machine. They might be consuming a lot of CPU and causing other tasks to become starved for resources. And when we wanted to do new things, we wanted to try new stuff, we wanted to try a new scale that we hadn't operated at before, it was a manual process to go in and provision larger machines into that cluster in advance, knowing what's going to happen, and again pay for those machines on demand. So there was a lot of downsides to what we were doing, but as with everything, simplicity won out early on. But eventually we need to graduate to something better over time. So we started evaluating different options for what we could do to solve this problem. And the most important thing, I learned this from a really good talk from someone at Amazon, was that you need to make sure before you come up with any ideas and before you plan anything that you have planned out a objective way to measure whether or not an idea is good. It's not a case of putting out all your ideas on the table and then just deciding after the fact that one's probably going to be the best. You should pre-plan sort of what it is that criteria is that you need to meet for success. So for this project, we came up with a list. The first one was something we couldn't already do that we needed to be able to do, which was to support different machine configurations. So different number of cores, different frequency of cores, different amounts of memory. We needed to support massive parallelism. So with Polymathian's growth into the simulation space comes a desire to run dozens or hundreds of these computations in parallel with a single click. And that's something that we would struggle to do with a pre-provisioned amount of compute without massively over-allocating. We needed to be able to limit an individual product or user. That's more of a business requirement than a technical one. But people pay for a certain amount of licensing, and we have to make sure that they can't exceed that, essentially. One of these, number 4, which I'll come back to because it became quite a theme with the one we ended up choosing, was that it can start up within a reasonable time. If you have a user that clicks a button, and most of our users sit and watch these things happen for the shorter ones, if they have to sit there and stare at a blank screen for a quarter of an hour while a cluster is spun up and pre-provisioned and all of that kind of stuff is completed, they're going to be pretty annoyed by that. And even if it adds a lot of performance to them to outweigh the startup time, it's going to feel slower because they're sitting there staring at a blank screen. Of course, it needs to be highly available. It can't just go down because some servers fail. And when we were sort of benchmarking this, we looked at our past usage patterns. And we decided about 100 tasks a week was an average for these larger scale computations. And that workload was quite bursty. And I'll come back to why that 100 a week was important. I won't go through everything we looked at, but I'll cover sort of get more technical with what we actually ended up doing. So what we made was an API, Task Manager API there on that diagram. And it is called by the existing web application. The web application sends through a definition of the task it would like to run to the API. The API checks all your rate limits, manages queuing, all that kind of stuff. And then it utilizes the cloud and the burstability and the scalability that the cloud gives us to launch up EC2 instances within AWS on demand for that run. So every time you go into one of our products now and you hit run, that's an entire virtual machine being spun up just for your task, just for you, and you have 100% utilization of it, and then when you're done, it turns off. So the specs are based on the task definition. The product developers will say, my task needs about 10 gig of RAM and 2 cores, or 200 gig of RAM and 38 cores, and the API will look at what's available within AWS and find the most cost-effective machine type that satisfies those requirements. And then it injects into that machine a customized startup bash script that implements a whole bunch of stuff. The biggest one being that it pulls down the application code, runs that within Docker. It does a whole bunch of other stuff too. It starts up some background logging management, performance management, and monitoring software. So then that sits there. The worker is running away inside its container, and the monitoring code is sending back performance statistics. It's sending back logs and stuff that lets the product developers be able to better understand the resource utilization. And the eventual goal there is to be able to potentially do some sort of either algorithmic or even AI-based analysis of previous inputs and how much resources they actually used and how much time they took. And that could be something quite cool to expand on in the future, where you could give users predictions of how long a task is going to take, and on our end predict how much resources something's going to need just based on the size of the task that the user created, which again is something we can't know in advance. They could just decide they're going to make the task twice as big this week, and we have to deal with that. And then there's some systems there to send logs and user-facing output straight back to the user, and they can sort of see what's going on. And that worked quite well. For the most part. I'll sort of start with the good. So this chart here that you can see is one of our internal performance charts, and the purple line going up the middle is memory, and the blue lines each represent a core, the CPU utilization of a core. So this solve is something that we couldn't do before. This is a 360 gig machine with 48 cores running for 2 hours, not 2 days, that would be a lot, running for 2 hours straight. So that was something we were never able to do before. We were limited by the capacity of the machines that we pre-provisioned. And to pre-provision hundreds of gigs of RAM and dozens of cores, 24 hours a day, 7 days a week, probably would have bankrupted everyone. So that wouldn't have been a good solution. It also gives us the ability to do some other stuff that we didn't realize was really good. Something we thought initially that was going to be difficult was the ability to inspect these machines. So with the previous solution, you can just SSH in, you can look at the files, you can go, oh, something went wrong, what was it? But with these ones, when the task's finished, it's destroyed, and everything you didn't take off the machine is gone. So one of the things we did there to try and debug was actually just dumping the entire working directory out to a storage service. And that was meant initially as a debugging tool, but it actually became immensely helpful for developers to be able to go in and see more detailed input than they had access to before, and see what it actually was that was causing different performance changes. And on the back of that, people have actually managed to make their own software faster, thanks to this sort of more DevOps tooling. And the parallelism worked great. We did a demo, we had one button that started 100 tasks, and they just started up in parallel. It was fantastic until you hit the bad. So no solution is perfect, is I guess what I'm getting at, and there's no sort of, often there's no 100% silver bullet for every problem. So there were some downsides to what we ended up doing. There were startup times, that it takes time to start up an entire virtual machine, download a Docker container, connect to a database, all that kind of stuff. It's on the order of 1 to 2 minutes, which we agreed was acceptable for tasks that take quite a long time. But like I mentioned at the start, we also had this other category of tasks running on the same system, which were 10-second jobs to process a file. So what we ended up doing there was a hybrid approach. So we're keeping the old system and scaling down the old machines so that they are available for short, sharp tasks. And then we're keeping the on-demand system for the much larger, longer running tasks. Something else that was very unexpected, and it's something that it's hard to plan for, is that the entire thing was supposed to save us money. It wasn't the main motivator, but it was supposed to be a nice side effect. But because of an unknown latent demand that was already there that we hadn't really realized, once people had the ability to run more solves with more resources more often, they did. And we sort of predicted our usage based on a previous constrained environment, whereas with a new environment, people had more flexibility. So we underestimated by about 30 times. So that was quite a shock, and I've attached a chart there showing the number of solves. It's probably a little hard to read. But our original goal was about 400 solves a month, and by July we are hitting 1.2 thousand, and only about 50% of our products have picked it up at that stage. And in that first 3 months, some stats is we ran 2,500 tasks for just over 5,000 hours of compute for 56,000 CPU hours, and that's only at a 50% adoption. So now that we've been through that process, we're sort of at the tail end of this particular engineering challenge for us. And you're going to look forward and decide, what are we doing to do next? Is it complete, or is there room for improvement? And I like to think there's always room for improvement. So the big one is that startup time, and there's ways we can improve that. There was a great article posted in UQCS Slack the other day about reducing your Docker image sizes and container sizes, and that's something we've been pursuing very actively actually over the last couple of months. Is we found there was a linear correlation between startup time and image size. So working on reducing that will help improve that startup time and improve the user experience. And the other one was optimization of cost. So when we started out, we just picked a small cluster of AWS machines that we could draw from, but AWS provides a lot of different purchasing methods and machine types, and we could extend the API to understand those better and be able to make smarter decisions around provisioning your task in different places on different kinds of machines to do the same compute for less money, which will allow us to sort of, again, likely isn't going to reduce cost, it'll probably just increase utilization. So that's the end of that one. I am going to step off and hand over to Alistair, but I will be in the chat if anyone has questions.
Thanks, Mitch. Hey, I'm Alistair. I'll be taking you through some of the real-time stuff we do for one of our projects, Vault. So a bit about me. I'm a Vault developer at Polymathian, that's why I'm here. I've been at Polymathian almost 2 years. I started there during my first year at uni, and I'm still here and still at uni. I'm mainly responsible for infrastructure and app development of Vault. I'm a QUT student, and in my spare time I like to build robots, especially self-driving ones. Got a cool project at the moment doing go-kart. So About the Vault problem. So Vault is effectively a power and steam plant optimization tool, and it optimizes in real time. So the technical challenge involved with that is we need to know the state of the power plant in real time. This data exists, customers have this data, and it's in many senses across the power station, which the customers can read and store wherever they like. In this particular case, it's stored in an Azure data lake, and this data, there's a lot of this data, so hundreds of sensors with new data coming approximately every 30 seconds. So it's very tabular in its format, but we'll get to that in a sec, I guess. So the main problems we're trying to solve when we're working with this stuff is how do we get this data from wherever it is in our client's system and get it into Vault. And once we have it, how do we store it and where do we put it? So the short answer is use the internet, obviously. We can transfer using all sorts of AWS products. And our initial answer to storage was Postgres. And that is because of the great work Mitch does with the Tropify team. We already had native Postgres support in the Tropify framework, so that was a no-brainer. I'll give you a bit of a brief history of the iterations we went through when we worked on this stuff. And I'm going to focus on data streams first. So in the beginning, at the start of this project, the customer had an Azure data lake with most of the tagged sensor data in it. And what essentially happened was a cron-like job in Azure copied the data that we as Vault were interested in into a separate section that we could then access. But the problem with that, of course, is it was only able to run every 5 minutes because of limitations set by Azure. So Polymathian had to obviously poll that data lake, pull those files, insert them, and we could only get data every 5 minutes or so. So obviously it was very slow and effectively not real time. Takeaway from that is don't use files for real time things. The second version of this was we needed to get around Azure. And so what we had the client do was using existing architecture on Polymathian's end, we had the client push CSV dumps to a Polymathian S3 bucket. The benefit of this, of course, is there is no frequency limit. You can shove it as fast as you can, or as you want. But it's still file-based format. So as you can kind of see here, the data was still being batched up at some rate, put into their database, dumped out, and then sent to us. We had to grab it and put it into our database. So there's still a decent amount of latency, as well as it's batching what is inherently like event-based system. So that brings us to our current solution, which is SQS. So SQS, Simple Queue Service, is an Amazon service that allows, well, it's not much to it, it's a queue. At one end is the client, and they're putting tags on, and at the other end is us, Vault, who can read that data off. The benefit of a queue is that it is inherently real time. So as soon as a tag is generated in a power station, as something is read, it goes straight on the queue and makes it to us instantly. So that means we are it's asynchronous event based rather than being batched up over time. A bit more technical detail about how that actually happens. So we have in most of our apps a testing environment and a production environment, and that's the same in the with our clients. So what we do is we take we have two client-facing queues, which are for testing and production, and then these are both forwarded into Lambda, which is running in AWS, that has a bunch of routing rules in it. And these rules allow us to forward the messages to, and duplicate them to a bunch of different places. So production messages will obviously go to the production app, but they can also be replicated and sent to, for example, a developer who wants to also grab some of those messages for testing. So this routing gives us a lot of flexibility in what we want to do, and that will be important in a bit. So that's our kind of how we get and deal with this data. But then the second question we have is how do we store it? Where do we put it? So as I said before, we use Postgres in the beginning, and Postgres is fine. It's survived 2 deployments, 2 full deployments of Vault, and we're still currently running it. But we're starting to bump up against scale limitations. So, for example, to keep query times low, we have to archive old data so that you're not scanning a huge table. Doing this means that we're constantly rotating in and out old data, which means Postgres' auto vacuum is not happy and is constantly vacuuming just one table, and we're basically using an entire CPU for that. And due to this and some other reasons, we had to isolate Vault on a separate RDS instance, which is not something we normally do. All of our other apps are on one large RDS instance, which means everyone gets burst capacity of like the system, but like you're not all shoved into small tiny boxes. Everyone gets one big box. But because Vault was effectively being a bad neighbor, we had to isolate it. And we are kind of reaching the point where we either want to move back to our main RDS instance or do something else. We've found that if we want to move it back, we have to double capacity a load to accommodate Vault. So this is where Dynamo comes in. So Dynamo is a managed service from AWS. That means we don't have to worry about being a bad neighbor where it's completely isolated. And it solves a lot of the problems that we were inherently having with a relational database, which was as your tables grow, your access time grows. So one of the things that Dynamo guarantees is constant insert and access time, which suits our usage pattern better. It's also infinitely scalable. Take that word with a grain of salt, but it should support any new number of Vault deployments in the future with very little to no extra effort. There's also some other convenient features, such as time to live marking, which means we don't have to do our own archiving. And we're currently in the process of setting up a DynamoDB environment for Vault. So the process of that is basically we're taking live data and funneling that into our own custom DynamoDB setup to test against. The final point I would probably make about Dynamo is that it's not, so our NoSQL setup is not necessarily faster, but the main benefit we get from it is that we have guaranteed performance into the future. So as we grow and add more apps or add more data, we are guaranteed that we won't bump into these sort of issues again. So yeah, that's our setup, using SQS for channeling data in, and then we're moving towards DynamoDB as a NoSQL database to manage our real-time data. That's all I have. I'll hand you over to Jack to talk about Polymathian in general.
Thanks, Alistair. Okay, so I have the easy task of just talking about how good it is to work with Polymathian, what the company actually does, which is quite confusing on the surface, so I'll try to explain it in a little more detail, and how you can get in touch with us. And if we have time, I'll run through a particular problem we've solved. First, a little bit about me. I'm a senior manager at Polymathian. I've been at the company 5 years. I started the same day Mitch did, and I'm now the product manager for Vault. So I was involved in the development of that product from the start, which was about 2 years ago. And I've worked in a lot of other products we have, so in shipping, mining, and rail optimization products. I graduated from UQ in 2013, dual degree in mechanical engineering and science and maths, and eventually became a software engineer because I didn't like mechanical engineering. It says here my likes are C++ and Python. I like other things, not just those things, but they're the most appropriate ones to put here. So, what does Polymathian actually do? When I say I'm a mathematician, people say, where do you teach? And that annoys me to some extent, because there's a lot of maths around that is done by a lot of people, and we just happen to be a company that solves those mathematical problems professionally. So, the problem statement here is Polymathian helps industries save money by solving complex optimization problems with software, and we do that using techniques that come under the branch of maths called industrial mathematics. And so that the effort in the company is split between software development and consulting. So companies will come to us and say, I have this problem, we will either solve it with software or we will solve it for them once and give them a solution. That's what the consulting side means. So I'll sort of unpack these underlined sentences here and what that actually means. So there are a lot of industries that have mathematical problems. I'll probably go as far to say every industry has a mathematical problem. So at the high level, the industries we can work for are those where solving a problem a little bit better is worth a lot of money. So anywhere of the range of 1% upwards being an improvement in how the problem is solved is justifying our existence in terms of the money that it saves the company or the money that it brings in. So in terms of typical industries, mining, obviously a classic one. Mining has so many novel problems, and solving them even a little bit better can earn a huge amount of money. So there's a lot of software development and research in this area of maths is driven by mining problems. Rail operations. So planning rail operations is extremely complicated and is a focused area of research in this field of mathematics. So what drivers go on what trains? Where do the trains go? How do you make sure trains don't run into each other? Rostering and crewing is a particularly difficult problem in that industry. Another one is port operations. So if you think of any of the big ports in the world, like Sydney, Rotterdam, things like that, Singapore, the scheduling of what vessels move onto berth and off berth at what time, how are vessels unpacked? If you have 10 container ships that are unpacked in a row, where do you put all their stuff and how do you keep track of it? What's the fastest way to unpack 20 vessels that you have waiting? Things like that. Transportation, logistics, and network design. So that can cover a lot of things. Designing roads, designing airlines selecting routes to offer flights on is solved by this field of mathematics. Other types of networks will come later. Manufacturing is sort of one of the most original fields that use this problem during World War II. So a classic problem is machine selection. So I have 10 drills, 10 lathes, 10 cutters, and I have to make 400 widgets. How do I move them all through those systems so that I maximize the utilization of the machines, or I make the most widgets over time? That's the kind of problem that gets solved. Traffic management, as I discussed earlier. Telecommunications, so designing fiber optic networks. So if you can cover everyone's house with 20% less fiber optic cable, you will do a fantastic job and save a lot of money. Utilities, power pricing. How is power priced? The power that we're using right now is priced using an integer program in the type of maths that we use every day. And there are people like us solving those problems right now, every 5 minutes, in fact. Education, how do you allocate students to classes? how to ensure that the students want to sit together can sit together, the teachers that don't want to teach them don't have to, and things like that. That's another type of problem we solve. One of the canonical problems in this field of maths is portfolio optimization. So if you work for a bank, what do you buy to make the bank money? Do you buy gold? How much gold do you buy? Do you buy shares in other companies? And what is the best way to do that to maximize profit while minimizing risk? Another classic problem is sport. So NFL scheduling, AFL scheduling. AFL, the people who are doing the sport scheduling this year, I have a lot of respect for, because they'll be solving that problem over and over again with different coronavirus restrictions. But solving the NFL schedule, for example, is a problem that has papers published on it every year because of how complicated it is. And it takes 2,000 CPUs 2 days to come up with the solution for the NFL schedule. And politics. So how do you segment your voters into groups such that your resources that you have available in a minimal amount of time, you can allocate them to particular groups of voters to maximize the difference in an election? That's another type of problem. So returning to my original statement, almost every industry. So what kind of problems? Classic problems. These are like if you open a textbook, these are the kinds of problems you would see in this field of mathematics. So how do you schedule an airline? If I gave you 50 planes and 400 cabin crew, what do you do? Like, how do you make sure that cabin crew come home ever? How do they not just end up traveling around the world forever? There's kind of restrictions like that. The planes have to come back for maintenance periodically, every 3 months, say, for example. How do I make sure I don't get planes stuck in places that can't come back? And what is the overall objective of that? Am I trying to maximize the profit of the airline, or am I trying to minimize cost? That's a classic consideration. Mining is another classic example. So if you have a mining lease for a giant area in rural Queensland, rural WA, even in South America, there are quite small mining leases there. So say you've got a certain amount of gold under the ground. How do you get it out of the ground? If you know it's going to take you 50 years to get it out of the ground, how do you make sure that for years 0 to 20, you aren't just digging dirt out of the ground? Because you will need to have a lot of money today if you aren't going to sell any gold for 20 years. So that kind of problem is called an NPV maximization, net present value. I want my plan to give me as much money as early as possible. Another one is, how do I just minimize the duration of the mine? So I might just want to mine it all as soon as I can and then end the mine, so I'm not subject to price uncertainty in the future. And then the one I talked about before, which is the NFL schedule. So for the NFL schedule, you have to pick, for every game, you have to pick team A, team B, you have to pick the broadcaster, and you have to pick the stadium that the game is at. So 4 dimensions. I think there may even be an extra dimension on that problem. That is an extremely difficult problem to solve. And in that problem, what is your objective? What makes one solution better than another? Just any solution that satisfies all the rules is probably equally good as any other solution. There aren't, one isn't a lower cost solution. You're just trying to meet all your rules. So all of these things are called optimization problems, and I mean mathematical optimization. And so they're covered by it can be framed in a general way. And they're characterized by 3 things. An objective. So you need to be able, if you have 2 solutions, you need to be able to compare one to another and say this one is better. You can get algorithms to tell you that this is the best solution of every possible solution. And that needs to be done using some objective. So it might be maximizing profit. It might be minimizing cost. You can have 2 solutions and say this one has a higher profit than this solution and therefore it's better. You need a set of possible decisions. That's usually the thing you start with. So what are the levers that I'm allowed to pull if I'm solving a problem? So if I'm trying to work out how to run an airline, I may not be able to set the routes. The routes may be, contractually, I may have bought the routes, I may have bought capacity at Heathrow Airport, but I'm allowed to land a plane there once a day at 10 a.m. for the next 6 months. So that's not a decision I can make. The decisions I can make are what plane goes there, and maybe what crew go on that plane. So I need to understand very crystal clearly what decisions can actually be made. And then what restrictions are placed on those decisions. So I can only land 1 plane at a time, for example, at that airport. A solution that gets everyone moving around and moving the crew around and maybe maximizing profit will be to land 10 planes at the same time. But sadly, you cannot do that at most airports. So there are constraints that eliminate sets of decisions that can be made at the same time. Formulating and solving problems in this context in the real world is known as operations research. Strange word, but it's a field of maths. It's a major, you can do it at some universities. The term comes from World War II, was developed by the British originally. Strategic decision making, or logistical decision making. They were basically trying to work out where they should cache ammunition and reserves around so that they would maximize their utilization, and they developed this field of mathematics. That is the definition according to the UQ School of Maths and Physics. The mathematical study of resource allocation problems, decision, games, uncertainty, scheduling, and optimization. So, what about Polymathian? So, the company is Brisbane-based. It was founded in 2012. We have a presence in headquarters, obviously, in Brisbane, where our headquarters is, in Melbourne and in Perth. There's over 35 staff. It's a mix of software developers, software engineers, mathematicians, and consultants. A lot of PhDs in the company. We've grown to over 50 software deployments in Australia and across the world. And many of the tools we have developed or deployed to our clients have been industry firsts or industry leading techniques or solving problems that haven't been solved before because they were either too difficult or other vendors tried and couldn't do them. So we pride ourselves on being able to solve problems that no one else can solve. We will back ourselves to solve very difficult problems. It is an excellent company to work for. Every year there is a company holiday where we go somewhere as a group and have a good time. For the first 3 years, 4 years maybe, we went to Japan skiing. There's a lot of people in that picture, including the managing director. What is this a picture of, Mitch?
That's professional development. So I went to Sydney, went to Australia's AWS conference, and got to see some really cool technology before it came out.
Cool. Okay, so that's an AWS conference.
Yeah.
Cool. Yeah. So employees of the company get to do a lot of cool things, basically. And I love working at the company. I've worked there 5 years. I couldn't imagine doing anything else. I'll step back 1 second. 2 slides, in fact. I like working in this kind of environment because you get to solve different problems regularly, and you get to become an expert in a particular field very quickly. You need to be able to solve a problem in extreme detail, understand problems that people are solving at a particular company. You will do that for 6 months, and then you'll move on to something totally different. So you could be working in underground mining one day, learning how to dig a cave, and then a month later you'll be working on a power station. So I really enjoy being able to understand and learn to solve many different problems. Our tech stack. So at the lowest level for the mathematical calculations, the calculation engines are implemented in C++, obviously purely for speed. It was attempted to write them in Python early on, but there's problems that just cannot be formulated in Python that can in C++. And to solve the problems, we use solvers called Simplex and Groby. So if you Google them, you might learn a lot that you didn't know about before, because they're massive pieces of software used by a lot of people. Moving up the stack, for the backend and the website, there's Python. We have a framework that's built on Flask. We interact with our databases through abstraction, so through an ORM. SQL Alchemy being a fantastic one of them. I don't know what we would do without SQL Alchemy. Write a lot of custom SQL. Task management, we use RQ, and then for data input and output, so uploading files, exporting files. If there's queries that we don't want to write and put onto the database, we can pull the data into a pandas data frame and write essentially the joins and the computation in pandas and then present it to the user. So there's an interesting trade-off between how much pandas work you do and how much query work you do putting onto the database. And the browser, the front end is in TypeScript, React, and put together with Webpack. And then who owns the machines? Amazon does. So all of this stuff is running on, most of the time our AWS machines, but sometimes clients will give us their particular Amazon machines because they need their data to be on their machines. So, drawing to a close, Polymath is always looking for right staff. We try to hire very slowly and try to select excellent people and try to keep them in the company. We're always looking for part-time people and full-time people, and we'll usually continually interview people to make sure we always have people around, so when we need people we can turn them on when we need to. So at the moment we've got particular interest in recent graduates with Python experience, even more senior Python experience we're looking for at the moment. So if you want any more information, have a look on our website or email us careers@polymathian.com. That's all I have formally. I don't know if there's any.
Yeah, we've got a few.
Yeah,
Do you
okay.
have time? What? Yeah.
Good for questions? Yeah, cool.
Um,
Yeah, okay, go for it, yeah.
So we've got, first one from Jericho. Oh no, you got to answer.
I've got to answer the question, okay.
Yeah. First one from Jericho Limpin. Sorry if I pronounced that wrong. Hi Jackson, when it comes to finance, do you have an internal expert? I'm just wondering what kind of financial companies come to you.
Yeah, okay, so, no, so we have to become the experts. And that's an interesting one. So the finance one is interesting. So the data that, if the problem is important enough, in particular finance companies will have teams of people like us in their own company, and like airlines will typically have that. So where solving these problems is your business, then you'll typically have teams like us inside business. Some large mining companies have teams like us in their business. But the strictest answer to your question is no, we have to become the experts. So we have to become experts in the finance of a power station. You have to become experts in carbon pricing legislation because you need to be able to exploit it mathematically. And so what that means is working very closely with clients. So we will try to spend as much time face-to-face with them as possible. It's very difficult at the moment. And understand the problem that they are solving. We will implement it and then we will get people to validate it and verify it and stress test it. Because obviously, if there are tax involved, we can't sign off on an implementation of tax. We will need someone else to sign off on our implementation and then give it back to us. So no, that's why I like it. We have to become the experts in what we do as much as possible.
Cool. So we have two questions from Nicholas. What's the biggest optimization problem that you've worked on that has had the biggest impact? Money saved, time saved, etc.
Skirting on the edge of confidentiality. Probably strategic mining problems. So they're problems where you are looking at what is someone mining for the next 200 years, for example. And so you have a huge amount of flexibility. For example, the decisions you can make are just don't start that mine, for example. Or it might be all of these mines need to come online 10 years earlier. Or it might be there just aren't enough people to buy what you are going to mine in the year 2100. And so those problems, making solutions with a real mathematical approach, as opposed to guess and check, someone just evaluating a bunch of options. You can you can bank in terms of net present value, huge amounts of money, like hundreds of millions or even billions of dollars. Just because the set of decisions you are making is so big. That sort of contrasts with a tool that might be running every second and making decisions every second. But each decision might only be worth a couple of $1,000, but you are doing it every second. So in terms of the problem that is solved, it's worth $5,000, but you solve it every second for the foreseeable future. So those kinds of problems have real value, bankable value, whereas the problems you're solving in a strategic space, eventually you hope they'll have a huge impact, and mathematically they say they have huge gains, but on paper they have the bigger gain. But the problems that are solved in real time every second may be smaller, but over time they will accumulate more. Vault.
And maybe more for you, Mitch, from Nick as well. How do you deal with Flask at such a large scale? Are there patterns that make it a little less messy / ad hoc?
That's a very good question. We sort of have the benefit of the fact that we have very large scale products that provide a large amount of value to a very small number of users. So we'll go into a very large Australian company with hundreds of thousands of employees, and the actual target user base for us is probably on the order of about 10 people. So it's a very different kind of world where you're providing a very, very high level of performance and a very, very high level of availability, with always striving for 0% downtime and usually getting it for maybe a couple of thousand hits a month by 3 people. It's very, very different to what you'd imagine pushing limits of Flask to be. That said, we do push the limits in sort of unusual ways, and often they can be the harder ones to fix because they are the ones that are usually on Stack Overflow. So the limits we often run up against are request time or response size, because of the sheer amount of data we're dealing with and trying to then break that up. And also because our products are meant to be generic and reusable, we don't know what the next customer is going to throw at it. They might have a data set, something unlike we've ever seen before, and we've engineered for a certain number of meg upload. And they might have something completely different. They might have full geospatial data that they want to bring into the product, and you can't just handle that in a Flask upload. It'd be a disaster. So yeah, we don't hit the traditional Flask limits, and where we do hit stranger limits like that, we tend to then reach outside of Flask for something else. So in the case of files, we'll reach for direct S3 uploads. In the case of queuing data, we'll reach for WebSockets, often as a managed service. Or we'll reach for something where we've got high velocity in our real-time tools. We'll step away from Flask and use some sort of C-based program. A really good example of that is a piece of software called WebDis, which acts as a push cache where you can pre-compile your pages, push them into Redis, and then it will act as a web server on top of Redis. So that's what we do when we've got that very high volume. Yeah, so we do push Flask, but in an unconventional way. There's an answer to that.
That's all the questions we've got in there.
Cool.
As I said, if you have any questions, just email us. Or if you'd like to apply, if you'd like to work for us, send us an email at careers@polymathian.com. Otherwise, thank you everyone for watching.
Alright, thank you so much for the talk. It was really good to get insights into, oh sorry, I need to move into camera. Really good to get insights into the different problems you solve and the ways you solve them. So here's a mug.
Oh, thank you.
Now we will get 2 more, sorry about that, but yes, all
left-handed.
Yeah, left-handed.
Yeah.
All UQCS speakers are entitled to 1 mug, so yeah, that's our gift to you. In terms of the calendar for the rest of the week, we have tomorrow the competitive programming group from 5 till 7, and we will also have the Refugee Talent Australia talk on Thursday night. So thank you everyone for watching, and we'll see you soon.